Okay, so in this video, we're going to look at reduction of order and repeated roots. So reduction of order comes from repeated roots. So we're going to start off with our normal example like you're used to, right? And in this problem, we're given that we have to use reduction of order. Because the reason why I implement that into this problem is because sometimes you'll have repeated roots, but it'll just ask for the general solution. It won't actually ask you to use reduction of order, and that's when you're able to use the shortcut method. But I highly recommend doing reduction of order first just to get the hang of it, and then we'll go into the shortcut method later. But I'll show you what it is first though. So let's we propose y is equal to e to the RT, just like we've been doing. Take the first derivative, second derivative, plug them back into our original equation, and that'll leave us with, if we cancel out all the e to the RTs, we're left with r squared plus 2 re to the RT plus r squared e to the RT is equal to 0. Oh, and I cancel those out in my head, right? So this is it. Now this factors out very nicely, right? So then we know that r is equal to -1 with a multiplicity of 2. Yep. So now, previously, we would have went like this. Remember? We would have defined our general solution right from that. We would have said C1, or let's do this. We would have said Y1 is e to the negative t, and Y2 would be e to the negative t. Because you can think about it like this. Right? R1 is that, R2 is that. They're both the same. But in this case, when we write it, we're going to write it like this. Sorry, that's Y1. We're going to add a t onto it, onto one of them. Doesn't matter which one, just a t has to be added onto one of them. And that's the shortcut method. So then you can write your general solution. You just add a t onto one of them when you have repeated roots. But now, if reduction of order will show us where that t comes from. So in this problem, we're asked to use reduction of order. So we have to show that we can use reduction of order. But this is a good little way to make sure that this is the answer that you get, in my opinion. Okay, so for reduction of order, we know that y1, or one of the y's, has to be e to the negative t. Okay, but now we don't have another r. So we're just going to go ahead, we can write down e to the negative t again, but some v is going to be there, some other variable, right? In this case, we know that you can kind of infer that v is going to be equal to t. But how do we get there? That's y2. Well, first of all, I'm going to come down here, and I'm going to solve for y2 prime and y2 double prime. So if we use the product rule, right, this would be negative v e to the negative t plus v prime e to the negative t. Yep. And then we have to do the product rule twice now for the second derivative. So then this will be v e to the negative t minus v prime e to the negative t plus v double prime e to the negative t minus v prime e to the negative t. And if you don't know what I just did there, this is basic calculus 1 product rule, right? After a while you get used to it, so I would take your time, maybe pause the video, go back, practice it if you don't know what I did there, if I went too fast. But anyways, now that we have these, I believe that's right. Let me just double check that. Yep. Okay, so now what we're going to do is we're going to take our original equation. Let me copy this. Take our original equation, and we're going to plug in original equation. Okay. So for y2 prime, we'll go in for y double prime. Sorry, y2 double prime, we'll go in for y double prime. So that's v e to the negative t. Now we have two of these, so these will combine. This becomes minus 2 v prime e to the negative t plus v double prime e to the negative t. So now we have our plus 2 y prime, so we have minus 2 v e to the negative t plus 2 v prime e to the negative t. We have one term left, plus y, so we have plus v e to the negative t is equal to 0. So now, what can we cancel? Well, this cancels with this. If you add these two together, they become 2v e to the negative t, cancels with this. And we're left with v double prime e to the negative t is equal to 0. Okay, so now this is, I guess, where people start to get confused. First of all, this e to the negative t will go away. We're going to use a substitution. We're going to use substitution where u prime is equal to v double prime. Hence, u is equal to v prime. So let's go ahead. So then this will be u prime is equal to 0. And now from here, we can now integrate both sides. So we'll be left with u is equal to c. If u is equal to c, that means that v prime is equal to c, because u is equal to v prime. So now we know v prime is equal to c. We can take the integral of this to get v. Because remember, for our y2, we have this v term here. We have to solve for v. So we have to take the integral. So v would be equal to c1 times t. We can call this c1 plus c2. We plug that back into our original y2. So y1 was what? E to the negative t, I think? Yep. And y2 was v e to the negative t. We're going to plug this into here. We get c1t plus c2 times e to the negative t. Now, in reduction of order, we're going to assume that whichever constant is with the t is 0, and whichever constant is without the t, is 1, and whichever constant is without the t is 0. So then y1 is equal to e to the negative t, and then y2 would be equal to just t e to the negative t, right? So then if it asks for the general solution, sometimes it just asks for the second solution. But if you want to write down the general solution, it would look like this. c1 e to the negative t plus c2 t e to the negative t. And if you go back up to our shortcut method, you see that's what we had before. And that's what we got now. So that's where that t comes from. Right? We reduce the orders. We start... Oh, also, another note. We want only v prime or v double primes left. No v's. So you see here we were left with just this v double prime. the v's themselves cancel out. So that should always be the case for reduction of order. The v should always cancel. And you can be left with a v double prime, a v prime, or both. Doesn't matter, but any v's, it's no good. Go back and try and fix it. But anyways, this is our general solution. But now what if it asks to find a fundamental set of solutions? Well, we have our y1, y2, so we just take the Vronsky of those two. Right? The Vronsky, if you remember from the fundamental set of solutions section on my video, it's the determinant of e to the negative t e to the negative t, and their first derivatives. This would be product rule, right? So then we multiply these together. That's negative t e to the minus 2t and plus e to the minus 2t. And then we subtract the multiplication of these two. So then that's minus, I guess that become plus because of that negative there. Plus t e, let me write it out this way. This would become t e to the minus 2t. That becomes positive. These cancel. Oh, wait a minute. Those don't cancel. These cancel. So then we're left with the Vronskian of e to the negative t e to the negative t is equal to e to the negative 2t. That is non-zero. So it is a fundamental set of solutions. Okay, that's the first example. We find the general solution and we determine if it was a fundamental set of solutions. And it is. Okay, so now let's go to example 2. For this one, I'm just going to find the general solution, but again, you can take the Vronsky again and see if it's a fundamental set of solutions. But you can see this one is a Euler equation, right? Oh no. Okay, Euler equation. Right, because we have the x squared with the y double prime and the x with the y prime. And no x with the y. So this is a Euler equation. So remember, for the Euler equations, we propose that y is equal to x to the r, y prime is r, x to the r minus 1, y double prime is r times r minus 1 to the x to the r minus 2. So now we plug those in, right? We substitute x squared times r squared minus r times x to the r times x to the negative 2. I just rewrote that term. Minus 3x times r x to the r, x to the negative 1, plus 4 times x to the r is equal to 0. Let's cancel out. So this cancels with this cancels with this, and all of the x to the r's will cancel. Oops. And then we have r squared minus r minus 3r plus 4 is equal to 0. So now r squared minus 4r plus 4 is equal to 0. And this would just be what? R plus 2 squared? Yep. R plus 2 squared is equal to 0. Make sure that's right. Yep, so far so good. Okay, r is then equal to 2 with a multiplicity of 2. right? We have two of them. Or you can say R1 is 2, R2 is also 2. Okay, so in this case, let's use reduction of order. Actually, let's do the shortcut method first. Okay, let's do the shortcut method first. So for the shortcut method, we know, okay, y1, remember, for this one we propose x to the r, right? So we have y2 squared. And for the second one, now if you recall back to the last video, remember how we included that natural log in there? We're basically going to do the same thing, kind of. So for the shortcut method, y2 or y1, whichever one you want to include it on, all you're going to do is shove an ln of x on the next to the x squared. So this is the shortcut method, so then our general solution would look like c1x squared plus c2 x ln of x squared, and that's our general solution. But now we need to use reduction of order, right? Because that's what it asks for. But it's a good way to check. Okay, so now remember, our y1 is x squared, and our y2 would then be vx squared. Take the first and second derivatives. Y2 prime would be 2vx plus v prime x squared. Y2 double prime would be 2v plus 2v prime x plus v double prime x squared plus 2v prime x squared. And the reason why I'm so fast at this is because I've done this a lot. Right? I've done the product rule many times. So I get really fast at it. So it just takes a lot of practice. Let me make sure that's correct before I move on. V double prime x squared plus 2 v prime x plus 2v. 2v prime, 2v prime x's, right? Yep, okay, we're good. Okay, so now we plug back into the original equation, right? So let me go back up here. Remember, we are going to substitute back into here. So we're going to have x squared times all of the y2 double prime. So that's x squared times 2v, x squared times 2v prime x, x squared times the v double prime x squared is this, and then x squared times that last term, x to the fourth, right? So I'm taking x squared, multiplying it by this, negative 3x, multiplying it by this, and 4, and multiplying it by this. I should really write those in red, right? What was that? X squared? Okay. Now we have the second term, so this is going to be minus 6. I'm multiplying negative 3x by this term here. So that's negative 6v x squared minus 3v prime x cubed. And we have one term left, plus 4vx squared is equal to 0. Okay, so let's look at what we can combine. So let's look at the x squared v's, because we want to get rid of v, remember. We don't want any v's. They must cancel. So let's try and cancel out these v terms here. So we have minus 6 plus 4 is 2, negative 2, plus 2 is 0. So look at that. They cancel. Now we have our v prime x cubes, right? So we have v prime x cubed over here and over here. Combined, that's what, negative v prime x cubed? And then we just have... Oh wait, I missed a v prime term. There's one over here too. If we add 2 to that, that's just positive v prime x cubed, right? And then we have this other term that's left, plus v double prime x to the fourth is equal to 0. So now from here, what, we can factor out an x cubed, right? Oop, that should be an x there. Now we're just going to focus on this part here, because we're just solving for v. Okay, so remember, we use our substitution. Remember, our substitution was u prime is equal to v double prime, and u is equal to v prime. So this tells us that we're going to have, I'm going to write down the second side first. So we're going to have u prime times x plus v prime, which is u, is equal to 0. Now we have to solve for u before we can solve for v. So we can, you should be able to recognize that this is separable, right? Because look, if we take this, du dx times x is equal to negative u. And we can separate that, right? So then this would be what? X dx is equal to negative u over du. Integrate both sides. This would be oh wait, I separated that wrong, didn't I? Remember, yeah, that was backwards. So we have to get, so see we have du on top here, so then this could be du over u is equal to, this multiply both sides by dx, divide by x. That negative is still there. So then this would become, actually keep the negative on this side. So let me show you what I'm doing here. So to separate this, I'm going to, because you see before when I separated this, sure, I get all my, I get everything separated, but the dx and du are on the bottom. You can't integrate when they're on the bottom, right? They need to be on the top. So we have du on the top over here. All I'm going to do is divide it by u. Now that negative is still over there, so I'm going to multiply by dx and divide by x, but that negative is still there. So this becomes the natural log of u is equal to the negative natural log of x plus c. Remember, exponentiate both sides to get rid of the natural logs. U is equal to, this would be e to the negative ln x plus c. Now remember, this just becomes negative natural log of x times c. I'll just write it there. This can be rewritten. Remember, this is the same thing as this, 1 over x. So then u is equal to c. Oh wait. Whenever you exponentiate a log, the log disappears, right? So you can rewrite this as, sorry, I did it correctly on the left side and messed it up on the right. This can be rewritten. And then this will become c times 1 over x. So then u is equal to c over x. Okay? If u is equal to c over x, then v prime is equal to c over x. And then we're going to integrate this. We're going to integrate for v. So then v is equal to c times the natural log, c1 times the natural log of x plus c2. Plug that back into our y2. Let me go back up. So if you plug this into here, this leaves us with y1 is equal to x squared. Y2 is equal to c1 times the natural log of x plus c2 times x squared. Now just like the last one, whatever is on either the t or the natural log of x would be set as 1, and the other one would be set as 0. So then that leaves us with y1 being x squared, y2 being the natural log of x times x squared. And if you remember the shortcut method, this is the same general solution. Sometimes, usually these problems, like I know in my textbook, it just asks for the second solution. So this could be what they ask for. Or they can ask for the general solution. So then you just write out c1 x squared plus c2 natural log of x times x squared. Right? And if they ask for fundamental set of solutions, take the Vronsky, and it should be. And this is how you do reduction of order. Okay, now I'm just going to end this video here. In the next video, I'm going to do one more example of reduction of order. But in this case, it's going to be a much harder problem that deals with a lot of ugly trig. And a lot of trig identities with integrals and stuff. So, and it's very long by the looks of it. So, see you in the next video.